So, uh, well, one thing you might ask is, to give sort of bigger picture, the physics project is something that sort of has emerged from a long sequence of adventures that I've had kind of alternating between basic science and technology development. It's always surprising to me the extent to which the things that have happened in that project were made possible by the kind of weird sequence of things that I happened to be exposed to first in kind of mainstream particle physics and cosmology in the late 1970s when I was kind of a kid, then in technology development of software systems, computational languages, and so on. Then in my adventures in studying simple programs and what they do in the computational universe, and just a whole series of pieces of that. The main ideas for the physics project kind of were germinated from this main point that I sort of discovered in the 1980s, that simple programs can do really complicated things, something that at first I didn't really believe. And it was kind of an experimental discovery from kind of actually doing simulations in the computational universe. And then later on, trying to figure out and getting the sort of intuitional idea that you could have simple rules, they would do very complicated things, and maybe that's relevant to the whole universe. And then getting stuck, as it turns out, in the exact same way that people got stuck a bit more than 100 years ago in thinking about the same question, which was, I only knew this, I only came to learn this recently. I mean, back, this whole question about is the universe discrete or continuous is a question that people have, talked about since antiquity. And people didn't have experimental evidence for that until the late 1800s, when it started to be clear that, yes, there are molecules, matter is discrete. Then one could think of photons, light can be thought of as discrete. But at the time, early 1900s, pretty much every self-respecting physicist was, whether it was Einstein, Bohr, Heisenberg, all these people were like, yes, space is discrete too, except they couldn't make it work. They couldn't figure out how to set up something that would be a thing consistent with relativity that would show discreteness of space. And they gave up. And in fact, I learned recently a piece of sort of science trivia that Heisenberg was all gung-ho on doing that, and eventually just said, this is too difficult. I'm just going to come up with the S matrix where I'm representing kind of the incoming states of an interaction and the outgoing states. And what happens in the middle is just something that I will abstractly consider, because I don't want to have to address these questions about things like discreteness of space. Anyway, so I was sort of stuck on the same reasons that they had been stuck on, although I didn't know they'd been stuck on it until very recently. Then in the early 90s, I started thinking about kind of graphs and networks as models of discrete space and so on. And by probably the late 90s, I'd figured out a bunch of things about that, although I still had a bunch of kind of hang-ups about things that could and couldn't be possible in I had an intuition about how things would work that I would say was inadequate. And finally, well, in the 2018, kind of came up with ideas about hypergraphs. And 2019, we kind of really launched seriously with Max Piskanoff and Jonathan Gorard into the whole adventure of the physics project, which went incredibly quickly. And the big surprise to me was that lots of things that I'd known for, I don't know, 40, 50 years and had been sort of mysterious, all seemed to have a way to fit into place. Now, so I'm very confident that the kind of underlying formalism of our physics project really has nailed it. Now you have to go from that to actual things that you can say about the universe and actually, do this quantum mechanics experiment, turn this telescope and look at this phenomenon. And that's a big challenge that I would say we're solidly, 50 years ahead of schedule on some of the conceptual things, and perhaps getting less, perhaps a little bit behind schedule in going from kind of the conceptual layer to the sort of practicality of, so what can you measure now type thing. One of the things, though, that's happened, so several things have been a surprise. One thing that's been a surprise was I was sort of initially kind of had the point of view, it's kind of, we have this model of physics and it's different from models of physics other people have and other kinds of developments in mathematical physics. And it's kind of us versus them, which is completely not the case. What has become clear, although many of the kind of connections still really need to be clarified, is that pretty much all of the seriously developed directions in mathematical physics, whether it's string theory or spin networks or even things with higher categories and so on, basically all of these things plug into what you can think of as sort of the machine code that we're defining. And I think that's something which, to understand that better, is super useful both for the developments that we're trying to make and for these other fields. And in many cases, it kind of tells one that the things that have been built as kind of castles in the sky of mathematical physics actually can have a grounding, even if they can't specifically say, oh, you'll observe this particle and that particle. At least they have some kind of grounding in a sort of machine code of what's going on. And partly what's, I think, happening there is there's a certain degree of conceptual universality in the things that are happening. And it's kind of like once you understand universal computation, you can realize that all these different particular models of how computers might work can all plug into that one idea. And I think that's sort of the kind of thing that's happened with mathematical physics directions and our project. I think the other things that are surprising to me, a couple of surprises. One is, I certainly had said, oh, we're doing this project, it's basic science, it won't have any applications for hundreds of years. That turns out not to be true, because it turns out that even at the level of using the project to understand things about distributed computing and very practical technological kinds of things, it's certainly been at least conceptually useful to me, and I think it will be, there's directions for it to be very practically useful as a way to sort of provide a framework to basically use the fact that lots is known in physics, and we can import the ideas of physics through the connection with computational kinds of principles. We can import ideas from physics, which have been pretty good, into kind of the things we want to do in practical computation, particularly when it comes to kind of parallel computation and so on. That's one thing. The other thing, which has been really kind of exciting to me, is the extent to which the ideas from the physics project end up being applicable to a bunch of other fields. So one that I sort of didn't see coming was foundations of mathematics. And I think, I wrote this book in the end about the physicalization of metamathematics, which I think is a pretty, it's sort of an exciting way to understand more about the foundations of mathematics, much to explore there that has really not been explored. Then, recently, for example, I've been applying these ideas to biology. Again, sort of a surprise, something that I had thought about in the mid-1980s about sort of why does biological evolution work and so on. I think now, using ideas that come from the physics project, I think we now have really interesting things to say about that. Then in another direction, understanding machine learning, one of the things that has been sort of a mystery is, why does machine learning work? I think we finally, using ideas that are sort of derived from the physics project, at least inspired by the physics project, have made, the last few months have made quite good progress in understanding sort of why machine learning works. And by the way, the story, sort of the conceptual story in all these things, wraps around this concept of computational irreducibility that I realize I invented 40 years and a few months ago. That idea, which I think by now, folks like you guys probably think it's obvious, which is good, even though there's still a stratum of people for whom it seems inconceivable. But kind of the idea that when you have a computational system, even though the rules may be simple, working out what the system does may be something that is sort of irreducibly difficult. You have to follow every step in the rules to know what will happen. You can't kind of expect to jump ahead and just conclude what the answer is. That idea is sort of a sharpening of kind of vague ideas that one might have about sort of complexity and things like this. It's kind of but it turns out to be, in that form, turns out to be really a critical thing in understanding lots of aspects of all these areas, from physics to metamathematics to biology. And another one which I'm hoping to tackle is economics, although I'm still in I don't know enough about the field stage. But the thing that has sort of emerged from the physics project, which is more of a conceptual thing, is the computational irreducibility, a fundamental phenomenon that shows up everywhere. But then there's sort of our nature relative to computational irreducibility, and particularly our kind of computational boundedness in the ways that we perceive things. And what is sort of become clear is that a lot of the story of why we perceive what we perceive seems to be the result of this interplay between kind of our computational boundedness and also things like our belief that we sort of are persistent in time and have this sort of single thread of experience. It's a very sort of philosophical ideas, but they are the things that sort of concretely seem to give one seem to explain why one gets the laws of physics that one gets. And it's surprising to me that one can go from these sort of, I don't know, vague philosophical sounding principles to something quite precise. I will say that the big excitement, as far as I'm concerned, is the idea that we can kind of derive the laws of physics. That from I was sort of from this concept of the Roolead, this kind of entangled limit of all possible computations, which is kind of a necessary, inevitable object that kind of, once you have the definition of terms, kind of has to exist. That knowing our nature as observers, you get to start deriving what physics we should observe. And to me, it's pretty surprising. I mean, the possibility of deriving the second law of thermodynamics, which is sort of one of the branches of the physics of the 20th century, that possibility people imagined in the mid-1800s didn't succeed in doing it. I think we can now do that, but that's sort of something which one could imagine deriving. The sort of derivability of general relativity and quantum mechanics is far less obvious, and certainly not something I'd expected, and something I think is pretty exciting. Now, to nail all that down, we need to sort of build a mathematical structure that lets us talk about the kinds of things that we need to really, fill in dot the I's, cross the T's on what's going on there. And for that, one has to start, I think, one has to rebuild a bunch of mathematical technology, starting from kind of, okay, we've got these hypergraphs and we've got limits of hypergraphs. And the question is, what does that mean about things like geometry? And so one of the projects that I'm trying to pursue right now is what we're calling infrageometry, the attempt to sort of reconstruct from Euclid on how one thinks about geometry when one isn't starting from something which is ultimately little patches of Euclidean space. And it is a little bit shocking that there's really nothing known about many of the aspects of what one has to figure out, whether it's what is a curvature tensor in 3.3 dimensions or something, or other kinds of questions like that. It's kind of a very greenfield area of basically mathematics to work out how that's set up. And I think perhaps it will be informal. I'm at this point, I think it is really a question of coming up with the right definitions and then having this sort of mixture of mathematical development and computer experiments. I should say something maybe about sort of the idea of computer experiments. This is sort of a methodology that I've kind of pursued for the last, 45 years now. And it's really worth learning how to do computer experiments. It is not, there is an art to doing computer experiments. It's like, how do you make how do you set up an experiment that's really clean, really simple? It's a bit like doing physical experiments or experiments in any other field. If you've got too much cruft going on, you'll never know what happened. You have to make a very clean experiment. Then you have to be competent at actually writing the code to do the experiment. And then another important thing is you have to just see what the results are. You have to not assume that you know the answer. I mean, I have to say, in the thing that is sort of shocking to me is after all these years of doing computer experiments, the same thing happens all the time. I'll say, I'll have some intuition about what's going to happen. If I didn't have that intuition, I wouldn't come up with the experiment to do in the first place. But I'll say, well, this system is too simple to be able to do this or that thing, but let me run it anyway. And it's important, the run it anyway thing is important, and you have to be sort of capable enough with the computational tools that in 15 minutes or something, you can basically get the thing running. Because if it was going to take you, 2 weeks to get it running, you probably wouldn't bother because you wouldn't have be convinced enough that you know what you're talking about. So kind of you run it, and you have to not, it's very important to get results from your experiment that are as direct as possible. Like people will often say, oh, I'm just going to do this experiment and I'm going to, filter down the results and I'm going to come up with 3 numbers. Okay, the problem is when you see 3 numbers, you can't tell what really happened. And often the numbers will be not coming from where you thought they were coming from. I mean, my favorite example from long ago was models that people had of snowflake growth, where they had very accurate numbers for the growth rate of the arms of a snowflake, but they never bothered to actually look at what shape the snowflakes from their models would be, and it turns out they would have been spherical. So that's kind of if you don't look at the details and you just sort of filter it down to 3 numbers or something, you will miss the things that particularly you didn't expect. So it's for me, it tends to be important to come up with good visualizations of what's happening, because visual things tend to be the highest bandwidth way to get stuff into our brains. And it's again, it's a sort of an art to figure out how do you make sort of the cleanest kind of presentation of what you're talking about. Another thing to know that one makes mistakes on, I try to avoid this mistake myself, is, you're doing a piece of work, you're doing these computer experiments, and you say, well, I'm just going to sort of hack together these things for now as I do the experiments. And when I finish it, then I'll make a more beautiful presentation so that I can show it to other people and so on. That's a mistake, because turns out the beautiful presentation is also what lets you see what's going on yourself. And so years ago, I had the experience many times that I would do things, I would sort of hack together what had to go on inside, and then I would be ready to, okay, I'm now going to make the nice picture to show to people. And then I'm like, oh, I didn't really understand this. I didn't see that in the hack together thing. I can only see that in the nicely presented picture. So it's worth, fronting that effort to sort of make things nice. And when you have the picture that just has a bunch of curves on top of each other where you can't see anything, that's a bad story. So in any case, but then the thing that happens is the way I usually put it rather whimsically is the computational animals are always smarter than we are. If you think this thing is not going to do it, it's not going to be able to do this or that thing, it'll find a way to do it. And when you look at it, it's like, oh, that's interesting. That's clever. I didn't think of that. But you discover that by being sort of open-minded in doing these computer experiments. And I think that's it is not trivial to get oneself to the point where you can just sort of do the experiments and then just look at what the results are and try to understand them and not sort of prejudge, oh, I know it couldn't possibly work this way. For example, my all-time favorite science discovery, this Rule 30 cellular automaton, I'm embarrassed to say that I generated pictures of that 2 years before I understood what was really going on in it. And I just sort of had assumed that a system that was that simple, whose rules were that simple, starting off from such a simple initial condition, I just assumed it couldn't really do anything terribly interesting. So I didn't really look at it in detail, even though I even published pictures of it. But they were kind of small pictures. And it took me another couple of years before I was like, and the end result reason why I did this was I thought I have this nice new laser printer and I'm going to try running it at high resolution just because I can. And then I'm looking at this picture and it's like, oh, this is not what I expected. Now I should understand what's going on. So that's another sort of thing to realize. I mean, another thing that I suppose is true of doing science in general is, one of the challenges is you do things, particularly you do computer experiments. Computer experiments are very nice because they're very reproducible. Don't forget to seed the random number generator, so to speak. They're very, you can show people, here's, in the things I write, there's click to copy code where you can just click on any picture, you get the code, you can run the thing again, and unless something went wrong, you can get the same picture that I got. And that's a very nice situation in science. It's unusual in science that you're able to do things like that. And it's a piece of kind of leverage that we have in this kind of computational science. But it's very reproducible, it's very clean, and the experiments will do what they do. The interpretations one might contest, so to speak, but the experiments just do what they do. The thing that is always challenging in science is, so you'll discover stuff from doing these experiments. Sometimes you'll discover things that aren't what you expected. Sometimes you'll discover things that that damage your prejudice about what should be true. And I think one of the things that I've found to be sort of an interesting, almost psychological issue is, can you get to the point where you're okay with where the chips fell, so to speak? If this works, it works. If it doesn't work, you go on. And there are cases, for example, in the physics project, where there were things that I had kind of had a strong prejudice against. For example, the idea that there are many histories of I as a person who's sort of I don't know, I like my thread of experience, so to speak, that I'm living on, so to speak. And I couldn't really, it was the idea that there would be sort of many threads of experience and many kind of histories for the universe had always struck me as being something, I don't like this. It just doesn't, I don't want that to be true. But then I realized, look, that was one thing. Another thing was I sort of didn't believe that the universe would be a totally profligate waster of computation, that it would have all these different paths of computation, absurd amounts of computation happening, most of which are irrelevant to us, so to speak. And it took me a while to kind of, for years actually, to get to the point where I'm like, okay, let's just imagine one could do it this way. What consequences does it have? And what I realized after I worked out some of the consequences is actually, in the end, it didn't even violate my original prejudices in the end, but it certainly looked that way in exploring it. But the thing that was sort of the challenge is to explore it anyway. I have to tell you one story from my early life in science, two stories maybe, that perhaps are useful to communicate. One is about inflationary cosmology. So back in, I don't know what it was, 1978 or something, I was working on cosmology meets particle physics with a chap who's become a pretty well-known cosmologist. And we wrote this paper about the expansion rate of the early universe. And I knew that if certain things happened, you would have exponential expansion in the early universe. And that would be a way to solve various problems that existed about why there would be homogeneity in the universe and so on. But I didn't really believe it would work that way, because in order to have that happen, the universe would have had to supercool by like 12 orders of magnitude. And I knew that any kind of imperfection and inhomogeneity, and I knew about sort of the sort of supposed randomness of quantum mechanics and so on, any inhomogeneity would blow that up. It wouldn't be possible. So we relegated this comment about, well, by the way, the universe could do this thing, we relegated it to a footnote. Well, I don't know, 6 months later or something, a bunch of people said, they'd read this paper in the footnote and so on. It's like, but that's such a good idea that, it can solve all these questions in cosmology, even though it seems totally implausible that, even though there might be a good physical argument why this is hard to achieve, it's like the payoff is so big, it's worth building the whole inflationary cosmology idea. Well, I don't happen to think that idea is probably right in the end. And I think in our models, there's a quite different kind of way that the same kinds of phenomena occur, from having a universe that starts infinite dimensional and then kind of cools down to lower dimensional and so on. But what the main thing there is sort of in when the payoff from thinking about something in a particular direction is large enough, it's worth pursuing it, even if you can't quite see how the steps go together to get there. Another thing I will tell you from my early life in physics, might as well pass on a thing which I think will be relevant to us as we go forward with the physics project, is my early interactions with experimental physics. So this was, I don't know, 1977, ancient times. I was working on QCD and I was trying to compute various kinds of, I was computing the rate of charm particle production and proton-proton collisions for anybody who's into those kinds of things. And I got a result. And there was an experiment that said, this phenomenon does not happen at a rate of, I don't know, 5 or 10 times below the prediction that I had. So what do? Well, the official line, if you're a theoretical scientist, is go back to the drawing board, you're wrong. The experiment says it doesn't work that way. But I just couldn't see how you could avoid this. You know, if QCD was right, and there was a lot of structure around QCD that kind of said it seemed to be what was going on, it was, you know, one just couldn't see what would happen. So I wrote this paper, I said, this is the prediction, and then I spent the second half of the paper explaining why this prediction might not actually be right because of what the experiments saw. Well, turns out the experiment was wrong. And it turns out there's a particular case. I mean, experiments tend to be hard. Frontier experiments tend to be hard. It's particularly suspicious when you have an experiment which says we saw nothing, because the question of how you're looking is a big question. And the way they were looking turned out not to be right. Well, so the lesson from that, experiments are hard, theory is hard. And, you know, you shouldn't, if you think the theory is strong enough, you should believe in it, even if the experiments are not necessarily, you know, even if some experiment comes back and says, no, that you know, that isn't right. And I think, you know, the other thing that I learned from that process was always go visit the experiments, go actually look at the thing. And I did that many more times, and I found horrendous things of kind of like, you know, you have a big effect, that effect is coming from a part of the phase space that you have no detector in that direction. The effect is some result of some Monte Carlo simulation or some such other thing. It's, you know, experiments are hard, and people, particularly I think in these large collaborations and things, all sorts of crazy stuff can happen. But the reason that's relevant probably to our physics project is there will eventually be experiments, and it will be a complicated thing to navigate. The question of what, you know, the early experiments will be hard, and they'll end up finding things that may or may not be correct. I mean, you know, the famous example of this is general relativity. You know, you may know the story in 1916, Einstein had made this prediction about the bending of light around the sun, and people went to go and observe that, and turns out they showed up in Crimea where there was going to be a total solar eclipse, right just when the US entered World War I, and they were sort of turned away, and so they didn't do the experiment. Had they done the experiment, you know, Einstein's prediction at that time was wrong. He just had not done the calculation correctly. By 1919, the calculation was correct, and this guy Arthur Eddington went off and you know, did this experiment. He probably fudged the experiment, and it agreed with the prediction, but he probably fudged the experiment. And you know, he had, and everybody was like, "Oh, it's all working great," although the experiment was probably fudged. I mean, the result is correct in the end, but probably not really established from that experiment. So it's a complicated, you know, there's a complicated dynamic which I'm sure we will run into with the physics project as it starts to hopefully engage with experiments. I mean, whether we are lucky enough, you know, in the late 1800s, early 1900s, turns out people were lucky enough that the instruments of the time could observe molecules. It's, you know, the scale of molecules is such that that was possible. It's not obvious we will be similarly lucky in things like the discreteness of space. It could be that we're, you know, off by 100 years in what kind of instrumentation is needed to observe those things. Well, let's see. I was yakking on about sort of how to do. So, I mean, this whole methodology of computer experimentation is one that I've found super useful, and it is kind of a way of getting beyond what you can imagine for yourself, so to speak. It's a way of a very clean way of kind of seeing what's out there, independent of what you can come up with your own imagination, so to speak. I suppose for me, the methodology that I've ended up pretty much adopting is sort of this mixture of do the computer experiments, do what one can of the kind of mathematical analysis and so on around that, using whatever methods one can. Sometimes one's going to run into computational irreducibility, and those methods just aren't going to work. But then the second thing is to sort of understand at a philosophical kind of zoomed out level what the key ideas are and how they fit together. And that's the thing that is a sort of another connection for our physics project, is I think there's an awful lot of philosophy that can be very interestingly done based on what we now have figured out from even just the structure of the physics project, regardless of all of the details of the technical aspects of it and so on. You know, I was struck recently, somebody was showing me Kant's antinomies. There's a list of sort of, the world might be this, you know, it might be finite or infinite, it might be discrete or continuous, it might be this or that or the other. And I was realizing that practically every one of these we now have something to say about. And that's pretty interesting. And often the way it comes down is something that's in between the, you know, it could be this or it could be that. That it's where, for example, in the, you know, discrete versus continuous, well, the underlying structure, the underlying sort of ontology for us is discrete, but the perception of it is in many ways continuous. And that's an important feature of our perception of the universe. That's an important feature of our sort of making sense of the universe, so to speak. So I think there's for me, you know, I have done a fair amount of study of history of science, history of technology. I have to say I find that much easier than history of philosophy, partly because, you know, in some sense in the history of science, even though, for example, history I wrote recently was about the second law of thermodynamics, which is a particularly tangled history that for some bizarre reason nobody had written before. Actually, it's not so bizarre. In retrospect, it is a really complicated history. But it has the feature that in the end, you can anchor that history to things which are fairly technical. It's like what got figured out, but you know, what did people understand, et cetera. For me, the philosophical history is more complicated because, you know, I read, I don't know, Kant, maybe not the best example, even, well, Leibniz, for example, another person with a lot to say about our kind of directions of things. And it's like, I don't understand this. It could mean one of 7 different things. And, you know, what I think it understands is often a back projection of what I now know, as opposed to more technical kinds of things where it's like, look, is the formula for entropy this or that type thing? So I found that very challenging, but it's something where I think it's really interesting, both for the philosophy itself and for kind of the suggestions that untangling that philosophy has for things that we should think about in the physics project, whether it's kind of this observer theory direction that I've pursued, which I strongly suspect can be informed by things that come from sort of philosophy people have thought about in the past, and so on. So, you know, I am just to mention some other things perhaps, and then maybe I could talk about some recent projects and efforts of mine, and maybe I should do that. Let's see. Is this going to work? I told you I'm not in my natural habitat, so this could be very very disjointed here. But anyway, so you know, I've been pursuing a variety of things, but these are some things that recently that just to give a sense of what goes on. I mean, there's sort of a mixture of things that are quite one thing I've been very interested in is these multi-way systems that we've studied, and kind of the ways to use multi-way systems to study different kinds of problems, and to use those problems to get more intuition about multi-way systems. And that intuition, I think, is important for understanding things about quantum mechanics and elsewhere. And so this is, let's see, somebody is perhaps sending me something in chat, which I can't read. So let me see.
That was just me giving you a halfway warning.
Okay, great. Thank you. Okay. Well, anyway, let me just mention perhaps some things I have been up to, and this observer theory thing that I mentioned is an attempt to understand kind of in our models, there's sort of the computational process, which is kind of the generator of things, and there's the observational process, which is the way that we take the things that are out there and turn them into things that we can perceive in our minds. And it turns out that features of that seem really important for understanding what it is we can perceive. And it's my effort to sort of formalize, as one can formalize computation in terms of things like Turing machines and so on, formalize the process of observation for the purpose of understanding its consequences for what one can observe. Let's see, I mean, this last year, this was sort of a big surprise. This was an offshoot of a project that about trying to answer the question of can AI solve science? Or is it the case that there are things that you can discover, for example, by computer experiments, that you can't expect the neural net is not going to have more intuition than we humans have, so to speak. It is, it is forced to kind of explore the reducible slices of the Rouliad effectively, as we humans do. And it doesn't get to sort of do irreducible computation, and one can kind of work that through, and it's sort of interesting. And by the way, and so one consequence of that was going back to something I had done in the 1980s of trying to understand biological evolution and trying to see, why does biological evolution work? Why do you get all these different kind of forms? Why do you get all these different sort of solutions to the problem of achieving certain fitness in biology and so on? And in the end, the story ends up being that biological evolution is effectively mining the computational universe, finding these lumps of computational irreducibility that it can harness to achieve certain fitness objectives that biology effectively has. So in a sense, it's making use of things where just there's computation that just happens to work that way. You don't get to explain why is it that this thing lives that number of steps. It just does, so to speak. And that has various consequences for the sort of foundations of biology and philosophy of biology. But the thing that actually that led to is thinking about the same kind of thing in machine learning, and the realization that in the end, machine learning is doing that exact same thing. It's kind of mining the computational universe for lumps of computational irreducibility that it can use for the purposes it has. So my analogy has been, imagine that you are trying to get a system that, you're trying to build a wall by some means. You can do that by engineering, where you make a bunch of bricks and they're all very nice shapes, and you can sort of assemble the bricks to make this very organized wall. Or you can do what machine learning is doing, which is to pick up random rocks of different shapes, which is kind of random lumps of irreducible computation, and find how you can assemble these things to sort of build your stone wall, so to speak. And that's a view of machine learning that sort of, it shows one why it works. It shows one why you won't be able to explain certain aspects of what's happening in it. Probably neither in machine learning nor in neuroscience will you be able to sort of explain, in the sense that you can explain why is that brick wall built up the way it's built up. So it's so anyway, one of the things that again is sort of a physics project spin-off is this effort to understand the foundations of machine learning. And then let's see if I can. I told you I have a weird setup here, so okay, there we go. Every so often I come back to do another piece of Rouliology. Rouliology is this thing, a recent name I have for kind of the study of simple rules and what they do. I consider Rouliology to be sort of a very fundamental science. It's kind of like there's mathematics, which has its particular kinds of things and axioms and whatever else that it studies. And there's Rouliology, which is kind of studying arbitrary, abstract, simple rules. And essentially, I think I've had this program that every footnote from the New Kind of Science book eventually is turning into a 50-page or more document. And this was a particular thing that was on a couple of pages of NKS, was this nestedly recursive functions. And so I decided recently to just figure out once and for all a bunch about how nestedly recursive functions work. It's pretty surprising. Again, it's sort of the story of what happens in the computational universe and the story of computational irreducibility, that definition is sufficient to give you that picture. And it's kind of like, what can you learn from this? And this is a case where you're kind of right at the edge of what is mathematically accessible. And so you can say some things mathematically, and that's an interesting thing to try and find the pockets of reducibility within these otherwise computationally irreducible systems. So I have certain rate of doing this kind of ruleology, and every piece of ruleology that I do turns out I sometimes think I'm getting too deep into this particular kind of system. Every time it's turned out to be useful. It's turned out that provides me sort of, oh, and now I know this example where when some phenomenon shows up, I'm like, oh, I've seen that before. I saw that in studying the ruleology of this particular kind of system, and so on. This is, well, that's a more philosophical thing about the nature of time that I think is kind of interesting. And this is sort of a ruleology meets biology study of things one can conclude from, I mean, there's a lot of things where as soon as you have this idea of multi-way systems, you know, of looking at all the possibilities, you might think, oh, it's just too big, but then look at a small case. But you start to learn things about kind of that whole sort of the interplay between all the possibilities is different from just following one or two of them. You know, in physics, one has been, you know, things like partition functions and so on are kind of partly the story, but you don't usually get to explicitly see, and you don't see the dynamics of what's happening there. So, for example, I am right now, let's see, what are the things that I'm working on and particularly excited about right now? There's a lot that is technological. One thing that happened technologically, boy, this is a challenging. Sorry, I'm just, okay, I might have to, okay, there we go. Technologically, and this might be useful to some of you guys, is this Notebook Assistant product that just came out a few weeks ago, which is kind of a build-up on top of LLM technology, combining LLMs with sort of computation augmented generation techniques and so on, to provide something where you can kind of just say something quite vague and it will try and write computational language code that crispens up your idea. I mean, I kind of see computational language as the notation for kind of thinking about the world computationally, just as mathematical notation is sort of the notation for thinking about the world mathematically. And this is, and so it's kind of the you know, computational language is sort of this way of expressing oneself that also has the feature that once you've expressed yourself that way, a computer can help figure out the consequences of what you're saying. But the Notebook Assistant is a way of helping one go from much vaguer things one might say to potential crispening up in computational terms. I should say, by the way, I think I made this list yesterday of things that are worth learning. And, you know, computer experiments, computer exploration, computational exploration, very worth learning. Kind of the computational exposition is another thing that's really worth learning. I mean, the idea of making a computational essay, it's what I do all the time when I'm working on things. I'm building up these notebooks that are essentially computational essays that have, well, maybe not as much text as they might, but at least headings and so on, and they tell a story. And when I can write good computational language code, which takes a little bit more effort than writing bad code, but the effort always pays for itself, so to speak, in the reusability of what you have and the fact that often writing the code helps you crispen up the idea and helps you actually understand what you're talking about more clearly just at the level of your understanding. So this kind of computational exposition of sort of learning to express yourself in computational language and just the mechanics of organizing your work as notebooks and as something where you can sort of record that narrative is really a useful thing to learn and to do in my experience. I think I had made a list of things to learn, and the other one is sort of the whole idea of computational thinking and these different kinds of intuition that particularly, well, both in sort of the what simple programs in the computational universe do, which is very surprising and very intuition breaking. And people, you will run into so many people who will just, their intuition will be like my intuition was 45 years ago before I really kind of sort of accepted what you observe in the computational universe. It's just like, it just can't work that way. Well, if you get inside and you kind of run these experiments, eventually you realize, well, actually it does work that way, even though that's not what our human intuition tends to suggest, because our human intuition, among other things, has a very you can't get something for nothing kind of motif to it. You can't just put in a simple rule and get all this stuff out. In order to get all this stuff out, you surely have had to put complicated things in. So that's kind of a really wrapping one's brain around that. Also, the kinds of things that come out from sort of the paradigm of the physics project, there's a way of thinking in that paradigm that I think is really valuable. And we have kind of this wonderful opportunity right now to sort of apply that to lots of different fields. And I think that's I see it as being kind of the 100-year opportunity because, physics, for example, had a very fertile period beginning of the 20th century and with a certain set of methodology that mostly came from the fancy mathematics of the time, whether it was Riemannian geometry or matrices or even things about partial differential equations, which by that time were decently well understood after things in electromagnetism and so on and fluid dynamics had kind of happened in the 19th century. So kind of there was a fertile time where you could apply the ideas of sort of these mathematical ideas to physics. And that's the typical pattern, I think, in the history of science, that, some methodology is developed, and then there's a certain amount of low-hanging fruit to pick based on that methodology. And that low-hanging fruit lasts for some number of years or few decades. And then it's a hard road for a long time after that until you get a new methodology. We are at a moment where there is a new methodology and a new kind of way of thinking about things. And it's really cool because we kind of get this opportunity to rethink a lot of the questions in fundamental physics, also a bunch of questions in the foundations of mathematics, which also had a fertile period right around the beginning of the 20th century. And it's sort of exciting that we get to do these things in these times, and not something I was personally expecting in my life, but it's cool that it's happened. I was talking about things I've been up to. I can show you, let's see, the thing I've been just working on most recently is a weird thing. Long ago, let's see, 25 years ago, actually, I discovered this fact, which is, again, one of these things that it's like, do you have the intuition to think this might be worth looking at? I was interested in what's the simplest axiom for logic, simplest way to generate logic. And it turns out it's so simple, you can just do a search and find it. And I found it. But to prove that it's correct was very non-trivial. And so in the NKS book, I have this 2 pages printed in a 4-point type that was the proof of the correctness of that axiom that I found with automated theorem proving. Well, in the years since then, kind of I've been, the question is, can you understand this proof? And that's something that's pertinent right now because there's a lot of interest in using kind of LLMs plus proof assistant systems to do mathematics, whatever that means. And this is sort of an extreme case of that. You've got a proof, here it is, you can look at it, it's on a page, but what is this? What kind of a thing is this? There's sort of a black box. If this is what proofs are going to look like, mathematics becomes an experimental like science, where there are a lot of black box results. You know it's true, but you don't know why. It's not kind of the white box approach that has been the one that people expect mathematics to follow. anyway, so I spent in the last couple of weeks, I've been spending a bunch of time trying to dig into, can I actually understand this proof? What can you do? And it's really complicated. I mean, this is kind of a representation of the interdependence of lemmas in this proof. And you can kind of see what's going on. There are these complicated lemmas. It's really hard to understand. You can check the proof. You can generate a proof function. You can run it. It's like, yup, the thing is true. But it's very, you can start seeing, well, there are these different lemmas that show up, and you can start looking at kind of the empirical metamathematics of what's happening in this proof, of what kinds of lemmas are how important in the proof. And remember, this proof is as generated by an automated theorem proving system, by the find equational proof function in Wolfram language. And it's sort of a strange algorithmic artifact. But it's sort of you can kind of start exploring. This is kind of the beginnings of the metamathematical space of sort of all possible theorems generated from these axioms. And you're building out this entailment cone. It's kind of the metamathematical analog of a light cone in physics. You're building out all true statements that can be deduced from these axioms. And then the question is, well, how do you prove particular ones? That's sort of a path finding, and that's what automated theorem proving does. But anyway, I've been exploring this question. Oh gosh, there's just all sorts of strange things about the innards of this proof, and how you can actually explore what's going on. And I've been curious about looking at all the different things you could look at. Is there a better notation for this proof? Is there a way of sort of simplifying the proof by not stating it in terms of this binary operator, but something else? Are there, what are the kind of popular lemmas that show up? Can you use those as kind of waypoints to sort of describe, just like in standard mathematics, you'd say, I'm referring to so-and-so's theorem, and everybody knows what so-and-so's theorem is, and so that's a way of kind of explaining the proof. Is there a way to find those things here? And so there's lots of, this is kind of empirical metamathematics meets ruleyology. Let's see if I have any other pictures that are fun here. Oh, this is a picture. This is sort of a philosophy meets AI meets, well, the Ruliad. This is an example of kind of the space, the generative AI image space around the concept of a cube. And so sort of in the middle is what you get from a generative AI generating a cube, but what surrounds it is the kind of interconcept space of things that are a little bit away from a cube in the mind of the AI. And that's a thing that, well, it's sort of relevant to understanding what kind of a thing in the mind of the AI could be sort of its explanation of what's happening in this proof. By the way, if you actually try using LLMs, they're fairly pathetic. I mean, they just say, they talk nonsense most of the time about this proof. And it's sort of interesting what you cannot get from at this point. Anyway, things I'm interested in myself. Infogeometry is another direction. Another thing that I've been studying is something that I'm surprised is possible, but I realized is possible, which is I'm trying to find a foundational formalism for medicine, which sounds like that's a crazy thing. How could you do something like that? Well, from this work on biology and this kind of studies of things that were evolved for a particular purpose, like these ones happen to live 100 steps and then die out, you can start asking, well, what is medicine about? It's about, well, we've got these humans and they kind of, they operate in a certain way, or they should operate in a certain way, and things go wrong. What do the perturbations on those evolved systems, what effect do those perturbations have? And how can you understand that? How can you sort of classify the diseases of these abstract computational systems? How can you understand the relative difficulty, the robustness to disease versus the difficulty of therapy, so to speak? And so I've been exploring, again, something I'm surprised you can actually formalize, but I think you can, these questions about sort of there are many questions that are quite practical. I mean, there are things about why are clinical trials hard? Because, you have this diversity of different kinds of organisms and consequences and so on. And you can see a bunch of these things in a very sort of minimalist way in these simple computational systems. So that's another sort of direction right now. Another thing that I really want to do is work more on the experimental implications of the physics project. As I say, I've been sort of hoping other people would do that, but I realized it's maybe harder than I expected. So I think that means I have to end up doing a bunch of that myself. I'd love to get help with it. They're both things in cosmology and astrophysics, looking for dimension fluctuations, trying to understand sort of is there a clever experiment you can do that's kind of like the Brownian motion analog for the discreteness of space? How does that relate to dark matter? I have some very definite ideas that just are difficult to work out about dark matter not being matter at all, but being features of the kind of microscopic structure of space. Well, I mean, sort of my favorite, in a sense, history of science pun is back in the 1800s, people wondered, what is heat? And they kind of said, well, heat flows from one place to another. Sort of that means that what heat must be is a fluid. And so they invented this kind of idea of caloric fluid. And turns out, of course, that's not correct. Heat is actually microscopic motion of particles. And then in modern times, well, from 100 years ago, when galactic rotation curves were studied and sort of the dark matter idea started coming in, people said, well, what can it be that affects the rotation curves of galaxies? Well, it's obviously matter, because that's the only thing we know that has a gravitational effect. It's sort of the same mistake as saying the only thing we know that flows is a fluid. And so my guess is that dark matter isn't matter at all. And my current guess is that it's kind of the space-time analog of heat. It is the effect, the large-scale effect of the microscopic, not quite motion, but the microscopic dynamics of discrete space-time. But I want to figure that out. I want to establish with the consequences of how you can see that residual effect of the kind of the change when you're in a gravity well of those microscopic effects versus when you're not in a gravity well. How does that work? It's probably a combination of simulations and theoretical analysis to figure that out. But also there's sort of the question of, is there just some very clever thing you can do with, some particular phenomenon about critical black holes or some other thing about, high energy jets and galaxies or something, some clever little thing where, like Brownian motion, which in the case of Brownian motion had been known for 70 years before its analysis, before it was understood what it was. But, is there potentially something which is already known where you can say, well, actually, if you analyze that correctly, you can see that it's sort of a microscope in the structure of space. So that's and then on the quantum side, I have this long time skepticism about sort of quantum computers and their practicality. The formalism is great. The investigation of kind of the physics of information and when it comes to things other than semiconductors is great. But the banner of, and now we have a quantum computer, I'm much less convinced about, sort of have been less convinced since I started thinking about these things in the early 80s, although I've tightened up my reasons for being less convinced. But my current hope is that if we could understand the sort of noise and other imperfections that people see in practical efforts to make quantum computers, that if we're very lucky, then what is seen there is a sign of what in the physics project is the maximum entanglement speed, that we will actually be able to, it's kind of like we're trying to make a telescope, we don't know about diffraction. Eventually, when we see that we have limitations on our telescope, we discover diffraction. If we're very lucky, the limitations that have already been discovered in quantum computers will show us something which will give us a clue about things about fundamental physics. So that's another direction I've been trying to understand. It's kind of like, it's always difficult when you are looking at experiments. I mentioned difficulties of dealing with experiments as a theoretical scientist. But one of the things is when you're looking at experiments and the thing that you think is most important about them is something that the experimentalists think is irrelevant. That's a particularly difficult case. I mean, that happened a lot in the things I've studied about simple programs. People had seen phenomena that are things a bit like the Rule 30 phenomenon, but they just sort of said, oh, that's noise. We don't care about that. Whereas for me, that was the main story. And so with quantum computers, if you go visit a quantum computing company, and I've done the field trips a bunch of times, although I need to do more of them, and they say, well, yes, we observe this noise. And you say, and they said, but we're going to get rid of it soon. We don't care about that part. You say, actually, that's the part that's most interesting. Let's talk about that part. But it's always the part they haven't really done much analysis on, just because it isn't what they care about. So it's difficult to sort of tease out, to get out of the trash, so to speak. That's the place where the most valuable things in some of these experiments, where you're looking for things that, one that I found in the, oh gosh, when was it? The 90s, was reproducibility of turbulence in fluid dynamics. One of the predictions of some of these models I've had is that the apparent randomness in turbulence will be precisely reproducible from across many hours of an experiment, or even between different experiments. And it turned out people had observed that, but they threw it away because they said that couldn't possibly be true. We can't publish that. People will laugh at us. And so that was a thing where, again, it's like in the trash is the most interesting thing, but it takes real work to sort of figure that out from the experiments and from sort of the practice of the experiments. So in any case, other things that I've been thinking about, the whole infrageometry story is one that I've been wanting to pursue. Another thing, oh yes, this is another one, is well, I got myself into a into a history project about the history of neural networks, because one of the things that came out of my study of foundations of machine learning is the realization that neural nets don't have to be as complicated as they are. It probably doesn't matter that you have all these connections and that you have these continuous numbers and so on. That stuff probably doesn't matter. And so I got to ask the question, which is something I often end up doing, when you're doing science and you say, well, this direction, the field seems to have taken the wrong direction here. Do you know what you're talking about? Well, one way to kind of confirm what you're talking about is to go back and look at the history and say, well, why did people take the field in that direction? And sometimes you realize, oops, that was something that happened for some very specific reason 150 years ago or something, and it really didn't make a lot of sense. It was because people had thought this at that time. Now we don't think that anymore. It should really go in a different direction. But it's useful as a grounding to understand that history of science. And so I've for example, my study of the second law of thermodynamics was for pretty much that reason, that I had a definite direction that I was pretty sure was the right thing, but I wanted to know, had other people kind of looked at that and decided it was a bad idea, or how had they missed that particular direction? They didn't have a bunch of the kind of conceptual apparatus from computation that we now have. But it was sort of interesting that people had kind of given up about 100 years ago, trying to understand some things. And that was something where you could sort of see them giving up. And then you could see people being confused because they sort of assumed that because people had given up, they assumed people had solved the problem, which they hadn't. They'd simply given up, which is a different thing from solving the problem, so to speak. So in neural nets, I got curious, how does it come to be the case that people made these assumptions about how neural nets work? The sort of main idea of neural nets dates from 1943, the work of Warren McCulloch and Walter Pitts. And so I've been trying to understand, why did they do what they did? And that's kind of led me to the Warren McCulloch's granddaughter, who was very cooperative. And I went and visited the still extant McCulloch farm and got big piles of books and things which the descendants were very happy to get rid of, and found some interesting material there that helped sort of fill out. I mean, it's always difficult. History of science is hard. I mean, trying to tease out what people understood when they understood it, not back projecting what we now know into things that people were doing then. But in the case of neural net history, it's quite interesting, because I found in 1873 people talking about kind of neural net works and sort of imposing logic on the nets of nerves in brains and so on. So, and there's even earlier stuff. I mean, Ada Lovelace, somebody I happen to have studied quite a bit, has a lovely quote, I hope to bequeath to the generations a calculus of the nervous system. And I'm not quite sure yet exactly what she meant by that, where that idea had come from. That was 1843 or so, I think. So I've been trying to sort of, in my efforts to understand why did neural nets go the way they went, I sort of have been reeled into this understanding this history, which is always challenging. And it's always particularly history when people are still alive and you can talk to them. I did some history recently about those nested recursive functions that I was looking at. And oh boy, it's so hard because that was Doug Hofstadter, was somebody who had worked on nested recursive functions. And I was the challenge of pinning down what happened when. Are you actually remembering that from 1965? Or is that actually something that you figured out in 1990? And you're kind of back projecting it to 1965. It's really hard. And in the end, it was pretty interesting what came out from that. But it's always for me, it's sort of history of science, a bit of a hobby. And I find it interesting. In any case, another thing I've been looking at is trying to understand the foundations of quantum field theory, foundations of quantum mechanics. Here's the thing, again, so when we started doing the physics project, one of the things I thought was, we're not going to understand energy until we understand particles. I was wrong about that. We can understand energy in bulk as this flux of causal edges through space-like hypersurfaces, or essentially amount of activity in our hypergraph. We don't need to know energy is in these lumps that correspond to particular particles. And so I've sort of assumed that in doing quantum mechanics and quantum field theory and so on, that similarly, we have to kind of understand particles. What are particles? What kind of topological structure or something do particles have in this network? Well, I realized recently that's probably not the case. And in fact, I realized that in quantum field theory, you don't really understand particles either. In quantum field theory, nobody makes a detailed model of the proton. You're not, when you're studying sort of interactions between particles, it's not like you have a great big carefully constructed initial condition that represents that whole particle. No, what you're representing are these point particles, these things where you're making Feynman diagrams and so on that represent the sort of histories of these things that are some shadow of particles. And by the way, this whole question about the preparation of initial conditions turns out to be a huge can of worms all over the place. So if you're doing general relativity, and you're trying to study black holes, which we're interested in doing in the physics project, preparing the initial conditions that represent plausibly two black holes, that's very hard. And you've almost already cooked some part of the answer by the initial conditions you prepare. Because in reality, in the universe, those initial conditions took a very long time to develop. You're not going to be able to reproduce that development. You're going to have to just say, I'm doing this experiment. It's, by the way, it's sort of a philosophical point that something that we intrinsically assume in science is that we can do whatever experiment we want. It might not be that way. I mean, the universe is doing what it does, and it might be that we are fated to only do the experiment that we're fated to do. That isn't something where we can arbitrarily pick. We're going to stick these two black holes where we say we're going to stick them. Could be you just can't do that. You can't. The details of how it got to that point will matter. By the way, I might mention one of the things. This is sort of a philosophy meets science story of one of the things. So there are many things we don't know about physics based on the physics project so far. So, for example, we don't know why space appears to us more or less three-dimensional. One of the things that I suspect is that the more we know about what we are like as observers, the more we will realize why the universe is necessarily perceived by us to be the way it is. Why we actually think of space as being three-dimensional, why we think of there being space at all, I think we understand that a bit from kind of the nature of us as observers, but why we're not sort of tracing the universe in some one-dimensional thing. Why we perceive three dimensions. My guess is that as we understand more about our nature as observers, including many things which are totally obvious to us, like that, for example, discrete objects exist in the world, or like that we can do any experiment we choose. We have sort of free will about experiments, or like that we believe we are persistent in time, which is sort of obvious to us. But it's something which, if you don't, by assuming that, you're already kind of determining something about how you perceive the universe. In any case, so one of the things that, okay, a recent realization of mine is that Feynman diagrams in particle physics, something I was a big enthusiast of when I was a kid, and in fact was one of the things that got me into using computers to do mathematical calculations and so on, because Feynman diagrams are really hard to compute. And Dick Feynman, who I knew pretty well, always used to say these Feynman diagrams are the stupidest thing, to work out, we work out all these complicated diagrams and then we get the answer, pi cubed over 7 or something. There's got to be a better way to do this, he always would say. In fact, I just found something recently that I'd written back in the, 1978 or so, in which I'd worked out the computational complexity of doing Feynman diagram calculations. And in the kth order, it rises like k factorial to the 5th power, which is kind of one of those really pretty bad computational types of things. But in any case, the thing that realized is, what is a Feynman diagram? It is essentially a causal diagram that represents the causal connections between interaction events. Those lines in a Feynman diagram that we interpret as particles, those are really essentially causal edges. And so trying to do a kind of a below particles approach to thinking about Feynman diagrams. And what I realized was, in quantum field theory, it's what you do as well. You don't have genuine particles in quantum field theory. You basically are just looking at the S matrix. You're just looking at, we've set up this set of very simple, initial conditions that are sort of plane waves at infinity or something. And then we're just seeing, then some interaction happens in the middle, which we can decompose in terms of Feynman diagrams, and then we get out some results. Well, I'm kind of, following the same principle and just looking at kind of these causal diagrams as Feynman diagrams. And I'm sort of optimistic that it may be possible, just like we could understand energy without understanding particles, we might be able to understand particle physics without understanding particles, which, as I say, is the hack that particle physics has also followed. It understands particle physics without understanding what particles are. It's a separate problem to understand what particles are, but that's proved pretty hard in particle physics. And that's something that we get to look at. And just as we're able to do these sort of simulations in general relativity, I'm sort of hopeful that we will be able to do simulations in quantum field theory that are more kind of honest simulations that people have been able to do in kind of Euclideanized space-time of lattice gauge theory and so on. And I'm really curious to see, just like we know some things about the field configurations of gravitational fields and things like black holes, what are the important field configurations in quantum field theories, and sort of what can one say, what is the sort of analog between, I don't know, fluid turbulence and quantum field theory. I should stop yakking in a moment here, but I do want to, what can I say to try and finish this off? I will make a comment that, in terms of just science worth learning and all those kinds of things, I was realizing that kind of thinking foundationally about things is the main thing that I try to do, with sort of the formalization mechanism being kind of this idea of computation and computational language and so on. But it's, you might think, well, you could just, if what you're really interested in is thinking foundationally about things, then you should just think foundationally about things. But it turns out that to do that, you just need to know a lot of stuff. And for me, it's been super useful to just know, to study all these detailed, specific kinds of systems, phenomena, and structures of ideas, because that's what you can kind of draw on when you're thinking foundationally about a new kind of thing. One thing to realize, which sort of I'm always noticing, is you look at different fields. You're looking at biology, you're looking at physics, you're looking at pure mathematics, you're looking maybe at economics, looking at philosophy, all these things. All these fields have different paradigms, different ways of thinking. They have different value systems about what it is that constitutes progress in the field, but they also have very different ways of how do you think about things. I was giving a talk a few weeks ago to a theoretical biology group, and I was showing these pictures of of all these cellular automata and these foundational kinds of questions. And it was striking to me that it was a person who was there at a theoretical biology seminar, and the person is looking more and more confused. And eventually they say, what kind of animal is this in? And it's kind of like, this is in that world, you're doing experiments, you've got rats, you've got mice, you've got nematodes, but you don't have just a thing that is running in a computer. It's a different, it's a paradigmatically different kind of thing. And it's so a thing that I certainly find useful is trying to sort of wrap one's brain around the paradigms of different fields. And I would say that in the physics project and things that have come from that, it's a new, well, I guess my title for my book from 2002 was A New Kind of Science, which was, I think, it's sort of funny that title seemed like a very gutsy title at the time, but I've had the experience now so many times where people are sort of talking to me about it, and like I'm on some podcast or something, and people are trying to describe what it is, and eventually they say, well, it's what is it? I guess it's a new kind of science. And it's like, yeah, that's why I called it that. But it has a different way of thinking about things, which comes from sort of computer experiments, the intuition from the computational universe and so on. The physics project has led to yet a different kind of multi-computational paradigm for thinking about things that I would say I'm still, I'm at year 5 in understanding that paradigm, and I'm still, it's early times. And what tends to happen, at least my experience is, eventually you really get to internalize these paradigms and think in terms of them, and then you start being able to sort of take the next step, so to speak. So anyway, that's a thing that, hopefully you guys can get some taste of here. All right, I think I yacked long enough. And if there are some quick questions or something, I don't know if we have time for that. I could do that. Otherwise, I look forward to chatting with you guys soon. And then I think we'll have all sorts of opportunities for discussion later on. But if anybody has quick, I don't guarantee to answer quickly, but if you have I'd be happy to have any sort of brief discussion. I was trying to give kind of a big picture story here. I don't know how effective that's been.
I
But
think
please.
what we're learning is that there are no quick questions, but hopefully we will have a complete session just for Q&A this weekend. And then, of course, this afternoon is the meet and greet where you get to actually interact with all the students and get to know them a little better.
I look forward to that. That's always super interesting for me. And I noticed I had written out some sort of outlines of, okay, projects. I know a bunch of you want to do that. This is challenging. We've kind of developed over the last 20 years this whole rhythm of doing projects at the summer school, which is longer. And I would suggest that it is more worthwhile to be able to do a project with some degree of completeness than to be able to do unless you're really going to be able to continue the project that started here, fairly soon thereafter. I would go for something where you really can think of it more as a research exercise, where you can do something that is new and different, hasn't been done before, but is within a framework that we already understand. I was seeing a list of potential projects, some of which are like, yeah, I know more or less how to do that. That makes sense. And some were like, that is very challenging. It's you're not going to get that far in a couple of weeks, and it might be better to do something, and maybe something that is a small part of that, that's more modest and more definite, and where you can do the computer experiments, see results, get a feeling for how to do computer experiments, and so on, and or get a feeling for some of the sort of paradigmatic ideas. I'm sort of encouraging modesty in project selection here, because I think we've with the summer school we're now 22 years of experience in scoping these projects. I would say that here it's like it's a really good thing to be able to do a project where you can wrap your arms around the whole thing, so to speak, rather than where you're where you're kind of, I'm not quite sure how to even start. If one heuristic is, if we don't know how to start it, it's not going to get finished in 2 weeks. So just making that suggestion. And I think, again, if you haven't done computer experiments and so on, it's really worthwhile actually doing some, because they aren't what you expect. And both, understanding the methodology, understanding the feeling of getting results you don't expect, these are really useful things to do. And people, it seems like, oh, that'll be easy to do. Well, it turns out it is quite easy once you know what you're doing, and it's pretty easy to get started even. But the kind of the experience is not what you expect, at least for anybody I've seen so far. Eventually there will be a generation of people for whom all this stuff is so obvious that it will all be what you expect. But for now, I think it still isn't.
There is one question in chat if you wanted to try to squeeze one in from Brian.
Let's see. Brian is asking, by studying the history of neural nets, do you hope to discover that maybe neural nets could have taken a different approach, or do you think it should have taken a different approach? Yeah, I mean, yes. Neural nets, look, they have a weird history. The fact that ChatGPT is pretty much based on the same ideas that almost McCulloch and Pitts had in 1943, more accurately Frank Rosenblatt had in the mid-1950s, is bizarre. The fact that really it's the same idea so many years later that hadn't worked for so long finally started working. And then people are like, well, of course that's how you do it. It's how we've been doing it since the 1950s. How could you do anything different than that? And now it finally works because we have faster computers, more training, and a bunch of engineering hacks. And so the answer is, I'm quite sure it could have been done a different way, with discrete systems, et cetera, et cetera, et cetera. And is that important? Well, actually, it's important in the on-the-ground wars of semiconductor companies, because there are, ones that have gone a long way in developing floating point capabilities. There are ones that have not done that, who seem to be just in totally losing positions. But if it turns out you can do all these things without floating point, all of that development of floating point technology is irrelevant for achieving what you want to achieve with machine learning. So, I mean, my current belief is that it's things like that. Walter Pitts, who was a young guy, 19 years old at the time when he was doing the work with Warren McCulloch, who was in his 40s at that point. Warren McCulloch was a psychiatrist, basically, neurophysiologist and psychiatrist. Walter Pitts was a kind of self-taught kind of math enthusiast who really liked things like Whitehead and Russell's Principia Mathematica and so on. Anyway, Walter Pitts had just been studying matrices, which were a cool thing of the time. And I think it may have been that fact that he happened to be studying matrices for quite other reasons may have been why he sort of introduced those ideas into the neural net thing. McCulloch, I don't think in the McCulloch-Pitts paper, I'm pretty sure that neither Pitts nor McCulloch understood the whole paper. They each wrote pieces of it. And it was, McCulloch was sort of on the more philosophy and biology side, Pitts was on the mathematical side. And I think they were sort of ships passing in the night to some extent in what they wrote. And well, then when Frank Rosenblatt came along in the 1950s, invented perceptrons, that was, I haven't understood that history as well. There are pieces of the history that are so bizarre. Like Marvin Minsky, who was a pioneer of AI, somebody I knew pretty well for many, many years, wrote a book called Perceptrons that basically destroyed perceptrons. Basically argued we can figure out everything perceptrons do, and it isn't very interesting. Okay, what I learned recently is that Frank Rosenblatt and Marvin Minsky knew each other in high school and didn't like each other. And and that's a piece of the sort of backstory that I didn't know. And then Frank Rosenblatt died young, and Marvin Minsky and Seymour Papert, the creator of Logo, among other things, wrote this book that basically destroyed neural nets for 20 years. And it was not until the early 80s that people started looking at neural nets again. And at that point, actually, I was a bit involved myself, and I knew all the characters who were in that business at that time. So I knew what happened in the 80s. And it was very messy and very kind of very empirical, and not really a moment when people were going back. And there was a lot of confusion about, were you studying this for studying the brain, or were you studying this for making computer systems? And it was all very messy. Anyway, so my guess is that this is a history that could have gone another way, and might have even been quicker. We might have even gotten to LLMs, 20 years earlier if it had gone another way. But there was enough training data from the early web to be able to do this, what we're doing now. Although there probably wasn't enough compute to be able to do the particular way of doing it right now. Although I'm not even sure about that. But yes, it's definitely a history took that turn for very capricious reasons. I mean, like that, Marvin Minsky and Frank Rosenblatt didn't like each other as teenagers and things like this. It was just the weirdest sort of sideshow to history. But that's the kind of thing you often find. I mean, I'm not about that particular point. I'm not sure. I need to talk to Marvin's widow about that to find out a little bit more if she knows more about that story, because I only have sort of fragments of that story from people who have access to grind in the whole story. So it's hard to, it's difficult. It's one of these terrible things, is that even, you talk to people, you think, I have it, I've got it solved because the person involved is still alive, I can talk to them, and it turns out that their memory is all scrambled, and sometimes they outright lie to you. And that's another whole complicated issue. And sometimes they think they're telling you what happened and they don't actually remember it correctly. And sometimes they outright try and throw you off the scent for one reason or another. And I pride myself on being able to not get thrown off the scent in these history of science adventures. But that's a different story. Well, anyway, all right. Look, I look forward to chatting with you all in a little bit. And thanks for being here, and hope to get to know you all.